So good morning. So thank you, the organizers, first of all, for organizing the exciting meeting. And Deepak, बहुत badai. Many congratulations once again. Okay, so I want to speak about finite time quenches in classical systems. And this work is done with Priyanka, who is a former PhD student and is currently a postdoc. Sani Chatterjee, who was a former postdoc and is currently a faculty. And I'm still thinking about this problem with Lakshita Jindal, who is a PhD student, is in the audience. Okay. So, so what I have in mind are systems that exhibit second-order phase transitions, and I'm thinking of only classical systems. So imagine a classical system which exhibits second-order phase transitions. If you like, you can think of an Ising model in 2 dimensions. So this system, because it has a transition, is a critical temperature Tc. And above Tc, system is in a disordered state, and below Tc, it's in an ordered state. So now imagine that we prepare the system in a disordered phase, and then lower the temperature instantly to either critical point or below the critical point. Okay, so that's the instantaneous quench. So as soon as I do this, the system is no longer in equilibrium, or more generally, not in the stationary state. And the question is, how does the system approach the stationary state? To take a specific model, here is a snapshots from the simulations of 2D Ising model when it is quenched from a high temperature to 0 temperature. So you see what you have is here, this white and black patches are upspins and downspins. And there are lots of these small domains of like spins. And then as time progresses, these domains coarsen. That is, the domain length grows with time. So this is the question that this is something one can measure and ask how the domain length grows with time. And I will denote that it typically grows as a power law. And I will denote that power by 1 by z CO. CO to emphasize that this is a coarsening experiment. Okay, so that's the very well studied problem, and it continues to interest people even now. Okay, so that's the instantaneous quench. I'm interested in finite time quench. So let me explain the problem. So again, we are thinking of the same system. Again, it is prepared in the disordered state, but now we go to critical point or below the critical point in a finite time tau. I should emphasize that now we are interested in the properties of the system during the quench interval. Of course, for instantaneous quench, you can only ask questions about after the quench, only the post-quench questions, right? Here, we are not asking questions after the quench. During the quench interval, what is the property system? That's what is of interest. And here are some, these pictures are from an experiment on this material, which exhibits, again, a second-order phase transition. This material can be modeled by a 3D XY model. So again, this system was heated to a very high temperature and cooled to room temperature. But this cooling was done linearly at different rates. So for example, here it's like 300 degrees Celsius per hour, and here is 0.5 degrees Celsius per hour. Okay. So in this case, the time tau, during which I took to go from high temperature to room temperature, was small. And you see a lot of these domains, and they are of small size. But when it takes cooling is very slow, time tau is large, these domains have coarsened, there are fewer defects. Okay, so in general, you expect that if I take a very long time, system would equilibrate, but at any finite time tau, somewhat largish tau, there would be more defects compared to if the system was in equilibrium. So therefore, that's the question, which again, typically one asks, that we expect that at the end of the quench, there will be more defects than in the stationary state. And but how does this excess defect density decay with the quench time? Typically, this also decays as a power law, and therefore, one is interested in asking what this exponent is. So there's a simple argument which allows one to find this exponent. So this goes by called the Kibble-Zurich argument. So let me, for simplicity, assume that the system is quenched in finite time tau to the critical point. So imagine we again started with the disordered state, and now I'm going to lower the temperature in a finite time tau. When I just started it, temperature has changed a little bit, but correlation length is of order 1. So system is able to relax. So although the temperature has changed a little bit, okay, And so therefore, the system is in equilibrium at that instantaneous temperature. Okay, so that's the situation when you are very, very far away from the quench time. But when the system is very close to the quench point, remember, because we are quenching to the critical point, there's a correlation length which diverges as we approach the critical point. So I have only 5,000 years when I'm going to stop my experiment. But this correlation, the relaxation time is of the order of 1 million years, right? So system will not, of course, relax. So therefore, you can think of these two limits. Time left till I finish my simulation or experiment is much, much larger than relaxation time, which is over here. System is essentially in equilibrium. Or when time left is much, much smaller than relaxation time, when system falls out of equilibrium. Okay, so there are these two regimes which are separated at a time t kz, where these two time scales are of the same order. Okay, so I'll be referring to this t kz a lot. Okay, so please just keep this in mind. It's the time scale which separates the equilibrium regime and the non-equilibrium regime, and it's the one where the time left, that is the time spent in the non-equilibrium regime, is of the order of the relaxation time. So that's what I've written here. So this is the remaining time is of the order of psi to the power zss. Okay, sorry, I forgot to say. So zss is the stationary state exponent. Okay, so that is the time scale associated with the for the decay of the stationary state fluctuations. Okay, so this will determine TKZ. How? Because I can also write now psi in terms of the temperature through this exponent nu, right? And now if I choose a cooling protocol, let us say this one, in which the temperature decays approaches TC algebraically, I plug it in all over here, and that will give me an expression for tau minus TKZ. So that's given over here for this protocol. So what this is telling you is, except for beta goes to infinity, the time spent in the non-equilibrium regime is sublinear in tau. Okay, okay, and then of course this is the length scale. Okay, so that's the sort of the very basic thing, and you can easily work out this a bunch of exponents that will come out. Okay, so what we started asking question about the residual defect density. So this now we will use to address that. Okay, so now if you're now thinking of a system when it has just fallen out of equilibrium, but I'm still changing the temperature. It had fallen out of equilibrium, it is trying to relax, and it had some defects already, and temperature is still changing, but the defects are not able to relax. So actually the dynamics are very slow in this non-equilibrium regime. So in fact, I'm plotting here the defect density as a function of tau minus t. So tau was the time at which I stopped the quench. So we are coming here from short times are over here, that is temperature is high over here, temperature is high over here. So there are a lot of defects, and as the system approaches the critical point, the number of defects reduces, but then you see, at least on this graph, this defect density looks essentially a constant. Okay, so to first approximation, one could just say that let's just completely neglect the dynamics in the non-equilibrium regime, and these dynamics are frozen at this special time TKZ, and therefore the defects that we had over here, the same defects, they just remain at the end of the quench also. Okay, so it's an approximation. So let me repeat. It says that excess defect density at the end of the quench scales as the excess defect density at TKZ. And that just dimensionally should be psi to the power minus d in d dimensions. And I already told you what the psi TKZ is, and you can write down this formula for your favorite quench protocol. Okay, so this is a standard thing, and this has been verified scaling. This scaling has been verified numerically, experimentally. In fact, the experiment that I showed you there earlier, you put in the relevant exponents, and it's consistent with the scaling. Okay, so that's the standard, very well-known story. Okay, but of course, nobody, will agree that dynamics are frozen. Of course, spins are flipping. Of course, something is happening, but it's a good approximation. Okay, so therefore, one would like to know what are the dynamics in this non-equilibrium regime? So that's a central question. Okay, so there has been some work, and let me explain what we expect and what is known. So suppose now we do this finite time quench to the critical point. So Leticia and colleagues have proposed that why assume that correlation length remains constant? It keeps growing. Suppose you say that, then the psi will grow with this exponent, and this is with this correlation length exponent for in the non-equilibrium regime. So that at the end of the quench, however, you will just get tau minus tkz to the power 1 by zss, right? So that scaling will remain the same as you expect from the standard Kibble-Zurek argument. But because correlation length is growing, defect density will reduce. So their prediction is that if you assume the dynamics are frozen, there is some defect density that you expect at the end of the quench. But now if you assume that the correlation length is growing, you expect smaller number of defects. So therefore, what will change is expected to change is just the prefactor. However, you can think of other protocols, like for example, the one that I showed you earlier. Here, beta goes to infinity is the instantaneous quench case. So I expect, therefore, that the coarsening also should play some role here. So therefore, one proposal is that the defect density is controlled not just by the correlation length, rather the domain length. And if I do that and just repeat the same math, you just find that the scaling can also be different. So the systems for which the correlation length exponent is different from the coarsening exponent, and when you quench the system to the critical point, scalings could be different. Okay, so these are all proposals and expectations. Furthermore, if the system is quenched deep in the ordered phase, then when you're very far from the ordered phase, the correlation length has become constant. It's no longer a relevant variable. What matters then is the domain length. And then Biroli et al. Say that the defect density simply depends on tau through the coarsening exponent in the ordered phase. Okay, so because the critical region is irrelevant, this answer is the exponent is expected to be independent of the cooling protocol. So these are all the expectations. So let me just summarize that on one page. So the proposal is essentially that treat the non-equilibrium regime as though an instantaneous quench has happened in that regime. And therefore, if you quench the critical point, you expect such a scaling, or if you quench deep into ordered phase, you expect this scaling. So these are proposals, and they have been checked numerically. So far, as far as I know, things are consistent with these proposals as well. But all the checks are numerical, and we wanted to see if we can work out some simple way or derive these from first principles. So that was the motivation for us to look at this problem. So for today, I will focus on finite time quenches to the critical point, and I'll consider two models. One is the Glauber-Ising chain, which turns out is solvable, and we can answer questions about the scaling function. For Glauber-Ising chain, these two exponents are equal, and therefore we don't expect new scaling, but prefactors can be analyzed. We can obtain expressions for that. The second model I'll consider is the mean field zero range process. In that case, we could not we could not get a scaling function completely. However, we find that the small masses and large masses, they have a different scaling. So let me just explain these points one by one. Mean field case? Yeah, so t equal to 0. So I'll explain. So this is the Glauber-Ising chain, ferromagnetic Ising model we are thinking of, and the Glauber dynamics is in this manner, that if you have these anti-parallel spins, the middle spin flips with a rate 1 plus gamma by 2, where gamma is tan hyperbolic of 2 by t, the t being the temperature, so that if the temperature is low, gamma is large, it's close to 1. And that makes sense that this rate is high because at low temperatures, you don't want domain walls, right? So it will try to get rid of domain walls. So therefore, this is the rate here. On the other hand, if the spins are already parallel, then flipping this occurs at a lower rate. And then diffusion can happen, which of course does not cost energy. So that happens at this rate. Okay, so this can be derived from the standard, you can look at Plower's paper and get derived this very simple way. It can be done. Okay. So this is the global dynamics. And what we do is to look at the spin-spin correlation function defined here. And this is known to obey this closed linear equation, even when temperature is time dependent. Okay. And the cool thing about this model is that it's exactly solvable for any gamma, even though it is time dependent. Okay. And this is known for a very long time, actually. But somehow, I don't know, these papers, especially Brain Prado, somehow seem to have been forgotten. So especially these guys, they gave explicit expressions for this correlation function. And they were interested in the scaling exponent for the defect density at the end of the Quench. But they don't seem to be aware of this Kibble-Zurek argument. So the answers are consistent with Kibble-Zurek argument, but they don't seem to have made that connection. Also, they did not analyze the scaling function.
So gamma depends on temperature?
Yeah, I'll come to the protocol.
And not on the time, no?
Not on the time. T is a function of T. Capital temperature is a function of time.
Okay. No, exactly solvable.
For when temperature is also a function of time.
Okay.
Okay. Yeah. Okay. So now to make some progress, I mean, to get some expression explicitly, I need to choose some cooling protocol. And this is the protocol I have chosen. I'm starting the system at T going to infinity, at infinite temperature, so that it's in a paramagnetic phase, and quench it to 0 temperature in a finite time tau. And this is how the temperature profile is. This is the expression. This is how it approaches at T equal to tau. I mean, you can think in terms of temperature, but what enters the equation is this gamma, tan hyperbolic of 2 by T, right? So for that, we assume that it approaches equal to tau algebraically with this exponent alpha. Okay, so that's this exponent alpha will keep coming. Okay. So that's the protocol. We plug it in, and we know, of course, the answers from Brain Prados, but you can do that, which we did. Or because we are interested in low temperature dynamics, what we can do is to just do the standard thing that we do in StatMech, namely try to find the scaling limits. So what we do is we ask that look at this object, the difference between the correlation function, the equilibrium one and the non-equilibrium, which I denote by F. Write down these scaling variables, capital K, which is small k times tau to the power minus A. So I want the distance between space to be large and tau to be large, such that capital K is finite. Similarly, I want the time to approach tau, but capital tau itself is large, such that Z is finite. Okay, so let's you plug it in your equations, write down the PDE, and find out the A and B, which will give you the scaling equations, the equation for the scaling function. So it's a straightforward exercise that one can work out. So from simple power counting, it turns out that the exponents that we get are same as what you expect from the Kibble-Zurek argument. Okay? So that's all nice. It's just that it's not a major point, but this is derived. It's not just by a simple, just not by using Kibble-Zurek argument. So this is derived. Okay. So then the scaling function obeys this equation. Second is a PDE, and one has to solve it using these boundary conditions and the initial conditions. And so one can do that. And of course, we know that's a doable problem. So it's of course easy to solve problem when you know that it's a doable thing. So what you can do is just take the sign transform, and then it's easy to just show that the answer can be expressed as a double integral of this form. And therefore, my task is simply to analyze this double integral. Okay. So the first question was, what is the defect density at the end of the Quench? So that is simply given by this fkz, which was a scaling function, so which we can analyze, and it gives me this expression. The scaling is same as the Kibble-Zurek scaling, because as I said, the exponents ZSS and ZCO are same. So the scaling is as expected. What is new here is this prefactor. So I think there's some interest in this amplitude. I think Krapivitsky was, the first one to sort of try to do this calculation seriously, but his expression is approximate. And there was also detailed numerical simulation recently. So of course, our expression matches with the simulations. And the reason why this prefactor is sort of interesting is because if I assume that the dynamics are frozen, that at the end of the quench, the ratio of the defects at tau and that of defects at tkz will be 1. But what this prefactor shows is it's not 1, it's much smaller than 1, right? So that's all. So it's just again saying the dynamics are not frozen, which you expect, but it is a sort of quantitative measure in some simple model. Okay. What about the scaling function? If I assume that now the correlation length or the domain length, they change in this manner, this would say that the defect density will approach the final quench time through this linear scale. Okay. But the detailed calculation shows that indeed that expectation is correct, provided this exponent alpha is large enough. Otherwise, there's a sublinear scaling. And a simple argument to see why that may be so is that when alpha is very small, system stays at high temperatures for a very long time. Almost at the end, it's like a small step function like behavior. It changes the rates very fast. As a result of that, the defect density, change in defect density diverges as z goes to 0. So there's a sort of a simple physical argument, but I'm not sure how to get this alpha plus half by a simple argument. Okay, how much time do I have? Oh, okay. Okay, so that's all I wanted to say about the Ising chain. There are more things which are probably calculable, but that's what we have focused on. Okay, so the second model I want to discuss is a zero range process. So in this model, you are thinking of a lattice model in which each side can be occupied by any number of particles, and a particle hops to a nearest neighbor with a rate which can depend upon the number of particles in that box. So that's U of M, M being the mass at that site. This hops can be symmetric, asymmetric, you can think into any dimensions and so on. And the cool thing about this model is that the stationary state distribution is known exactly. Furthermore, for certain choice of rates, there's a phase transition. So if I choose the rates to be this, then if okay, total density in this model is conserved. So if I fix myself at a density and I change B, this parameter B, then as B is increased, then system goes from a fluid phase in which each site has order 1 mass to a condensate phase in which there is one cluster which carries a finite density of mass in the system. And rest is distributed as a power law. Okay, so this is all the standard story, which is very well known and studied by many people in this room. I now try the same thing, that is just like we did for the thermal case. Now we say that this rate is, this parameter B in the rate is time dependent. Okay, so that's how we are quenching it. We start the quench in which B is 0, it's a fluid phase, and then take it to the critical point BC in this algebraic manner. Okay. Okay, so that's the quench protocol in this case. And because we are thinking of a mean field zero range process, then one can easily write down these equations. Everything is just P of M. There's no correlations and joint distributions and so on. And that's why we wanted to look at this model, in fact. So the equations are again closed, but they're non-linear. Non-linear because what comes also in these equations is this mean hop rate, which also depends on P. Okay, these are closed but non-linear equations. And we try the same thing as I said earlier for the Ising chain. I look for the scaling variables, define this capital M and capital Z, such that the small m is large and tau is large and capital M is finite and so on. Plug it in, work it out and so on. Okay, so then again, we find in this case also our scaling exponents are consistent with the Kibble-Zurich scaling. Okay, so, okay, and that happens because these exponents are again same. Okay, so far what I've shown you is things which were parallel to what was happening in the global case. The exponents, the scalings are same as the expected scaling. But there is one small thing which is slightly different. Okay, oh, sorry, let me just finish the story about large mass behavior. Scaling function, the PDEs can also be written just like for Ising model. However, we were not able to make much progress with it. So that's something which is still pending. But numerical indication of the PDE shows that the scaling function for small z is linear for sufficiently large alpha, and it's sublinear below that. So that, again, that kind of thing that we learned from Grover-Kiss holds here as well. But this little thing that I said is different. Is the small mass behavior or the fugacities behavior? So we know that if we do instantaneous quench critical point, then small masses, or the fugacity, it approaches the stationary state value through this exponent, t to the minus theta cap. Okay, it's a different exponent. It's not half or something simple. It also depends upon B, the BC. Okay, so inspired by this and our own numerics, for this problem, we made this kind of answers. Okay, just analogous to this. And again, we plugged it in our small mass equations and did power counting and so on. And there we find that the derived theta is same as if you think that the system is spending this tau minus tkz in the non-equilibrium regime raised to the power this coarsening exponent. Okay, so the basic idea was that you think of non-equilibrium regime as so there's an instantaneous quench in it. Okay, and this is also consistent with that basic idea. Okay, so that is all I think I wanted to say. I just gave you a couple of examples where some results in the non-equilibrium regime can be derived. We have also studied the one-dimensional zero-range process, and these experiments were found to be consistent with this instantaneous quench proposal, but this is completely numerically done. Now, right now, we're interested in also looking at the Kawasaki-Ising chain. The results that we get, we don't really understand. Okay, but I'm happy to talk to you if anybody is interested. And generally, of course, question is, can we get more analytical results? Are there simpler models that one can make progress? And very generally, I'm not aware of models which have a non-equilibrium stationary state where such a problem has been addressed. So only model I'm aware of is our own work in 1D zero-range process. So whether this finite time quenches can do something else happens if you have non-equilibrium stationary state, I don't know. I don't have any insight into it, but it could be an interesting problem to look at. I'll stop here. Thank you.
Kavita, do you think the regular zero-range process will behave the same way as the mean field?
Yeah, so that's what. So this is the 1D zero-range process also we studied.
Okay.
So the experiments were, only experiments were studied and they were consistent with this proposal, but it's completely numerical.
Nice.
And many things are not known there also, so it's kind of. For the mean field zero-range process, we looked at the mass fluctuations also. Right. Same story holds, but we looked at only the exponents. So what we would really like to do is to look at the scaling function, but we haven't been able to make progress with that.
Okay.
Thank Deepak and Kavita for this very nice session.